Something happened on February 14th, 1990, that most people have completely forgotten. A machine built with 1970s technology, powered by something barely stronger than a car battery, traveling at 38,000 miles per hour through the absolute cold of deep space, did something no human had ever done before. It turned around, it looked back. And in that single moment, it captured something so devastating, so quietly terrifying, so unbearably beautiful, that the greatest scientific mind of the 20th century reportedly wept. That image broke Carl Sagan, and then, 34 minutes later, the camera went dark. Forever. Or so we thought. Nobody told you the full story. That is the problem. You have seen the image. You have probably heard the quote, "The pale blue dot. Earth suspended in a sunbeam, reduced to a fraction of a pixel against the infinite black of space." You have nodded along and felt something vague and unnamed. But what you have never been told is what it actually cost to take that photograph, what it required, what was sacrificed to make it happen, and what happened to that camera immediately after, and why, and what that decision means for all of us living today, in 2026, nearly 5 decades after this machine first left the ground. Because here is the truth that the mainstream conversation always glosses over. Voyager 1 was never supposed to take that picture. The engineers didn't want to do it. There were serious objections. And the only reason it happened at all is because one man, one scientist who understood something about the human condition that pure engineering cannot quantify, fought for it, fought hard. Carl Sagan pushed NASA to command Voyager 1 to turn its camera around one final time, from a distance of 7 billion miles, and point it back at the inner solar system, not for science, not for data, for perspective, for humanity. And what makes this even more extraordinary is understanding just how absurd the act was from a purely technical standpoint. Think about what that means. Voyager 1, by February of 1990, was already beyond the orbit of Neptune. It had already completed its grand tour of the outer planets. It had already sent back the most detailed images of Jupiter's storm systems, Saturn's rings, the volcanic chaos of Io, the fractured ice of Europa. It had already done everything it was designed and funded to do. And now, at the edge of the solar system, with dwindling power and a mission rapidly shifting toward interstellar science, NASA was being asked to turn the spacecraft around, to point its cameras back toward the sun, an act that risked damaging the very optical instruments the team had spent years protecting. Because staring anywhere near a star is precisely what you tell a space telescope never to do. But they did it anyway. And that decision, that single moment of scientific poetry, produced the pale blue dot. On February 14th, 1990, Voyager 1 was 7 billion miles from the sun, already beyond Neptune and heading toward interstellar space, when mission controllers commanded it to turn its cameras back toward the planets it had left behind. The image of Earth that emerged was not even a proper photograph in the way we typically think of one. The familiar pale blue dot was a color composite assembled from 3 exposures taken through green, blue, and violet filters by Voyager 1's narrow-angle camera. Earth itself occupied less than a single pixel, less than a single point of light. And in that impossible smallness was the entire archive of human history. Every war, every empire, every invention, every love, every death, compressed into a fraction of a dot suspended in a beam of scattered sunlight. But here is where it gets harder to absorb. The NASA chronology is precise. The 3 exposures used to create the pale blue dot image were taken at 04:48 GMT. At 05:22 GMT, 34 minutes later, Voyager 1's cameras were powered off. They have remained off ever since, 34 minutes. The most emotionally significant photograph in the history of human spaceflight, and 34 minutes after it was taken, the cameras went dark. No ceremony, no final announcement, just silence and a deliberate switch, and the long journey into the unknown. Read that again. 34 minutes separated the most profound image ever captured from total, permanent photographic darkness, and nobody ever brought those cameras back online. Now you need to understand why, because the reason is not simple, and it tells you something uncomfortable about the nature of exploration and survival. Mission team members decided to turn off the 2 probes' cameras to save precious power during the long journey, and because they probably wouldn't have many chances to photograph interesting things out beyond Neptune anyway. That is the official explanation, and it is technically accurate, but it does not capture the full weight of what was happening. Voyager 1 was entering a phase of existence that no human-made object had ever entered before, the space between stars, the interstellar medium, a region so remote, so alien, so devoid of anything we can point a camera at, that images would have been essentially useless. Frame after frame of pure, absolute blackness, costing precious electrical power that could instead be directed at instruments capable of measuring the invisible. Magnetic fields, plasma density, cosmic ray particles, the very fabric of the space between solar systems. This is not chaos. This is strategy. Cold, rational, painful strategy. And the power situation was already serious. Voyager 1 Pris. Chase 1 is not solar-powered. It cannot unfurl panels and catch sunlight, because by the time it reached the outer planets, sunlight was already too weak to be meaningful. Instead, it runs on nuclear energy, specifically 3 radioisotope thermoelectric generators, devices that convert the heat from the natural decay of plutonium-238 into electrical power. When Voyager launched in 1977, those RTGs were generating roughly 470 watts of power. By the time the cameras were shut off in 1990, that number had already declined significantly. By 2025, the entire spacecraft was producing somewhere in the range of 250 watts, less than 3 standard light bulbs. And that number continues to fall at a rate of approximately 4 watts per year, with no way to stop it, no way to supplement it, and no ability whatsoever to refuel. Every single watt matters. Every instrument that stays online is an instrument that is slowly consuming a finite, irreplaceable resource. And every instrument that gets switched off buys the mission another few months of life. This is why the cameras never came back on. But here's the part that most people are not seeing, and it goes far deeper than just power management. In a purely technical sense, NASA says it might be possible to switch the cameras back on. In practice, there's no plan to do so. The controlling software was removed from the spacecraft. The ground computers once used to process the images no longer exist, and the cameras and their heaters have spent decades exposed to extreme cold. Think about what that means. The software that told the cameras how to function, deleted. The ground systems that would have processed the incoming images, gone. The computer infrastructure that formed the entire pipeline between Voyager's lens and a human monitor, dismantled, decommissioned, scattered to history. Even if someone at JPL decided tomorrow morning that they desperately wanted to turn those cameras back on, they would essentially be starting from scratch, rebuilding a technical ecosystem that no longer exists, to operate hardware that has spent over 3 decades in temperatures approaching absolute zero. And that was designed for a 4-year mission in 1977. The cameras may not even work anymore. Nobody knows. And that uncertainty is its own kind of grief, because Voyager 1 is still out there, still moving, still alive in the most improbable sense of that word. As of 2026, Voyager 1 is still transmitting from interstellar space, though on reduced power. It crossed the heliopause, the boundary where the sun's influence ends and true interstellar space begins, on August 25th, 2012, becoming the first human-made object to ever exit our solar system. That sentence does not get smaller the more you read it. The first object made by human hands to leave the solar system entirely. And it is still talking to us. Faintly, slowly, across an almost incomprehensible distance, but still talking. Right now, in August 2026, Voyager 1 is approximately 25 billion kilometers from Earth. The radio signals it sends home travel at the speed of light, the absolute speed limit of the universe. And they still take over 23 hours to reach us. One way. You send a command to Voyager 1 today, and you wait nearly a full day for that command to even arrive at the spacecraft. Then you wait another day for the response to come back. The round trip at the speed of light is approximately 45 hours. 2 days of waiting for a single exchange of information with a machine the size of a small car, built with technology from the Nixon administration. And this is where everything changes, because in November 2023, something went terribly wrong. On November 14th, 2023, Voyager 1 stopped making sense. The spacecraft, 15 billion miles from home, traveling at 38,000 miles per hour through interstellar space, and older than most of the engineers responsible for keeping it alive, began transmitting a steady stream of ones and zeros that meant absolutely nothing. The radio link was fine, the probe was receiving commands, it just couldn't form a coherent sentence anymore. For 5 months, the most distant spacecraft ever created by humanity was effectively speaking in tongues. The signal was there, the heartbeat was there, but the words had become noise. And the team at NASA's Jet Propulsion Laboratory faced a problem that had no precedent, no manual, no simple solution. You cannot send a technician to fix Voyager 1. You cannot ship a replacement part. You cannot even call it on the phone and walk it through a diagnostic. Every single thing that would be done to fix this machine had to be done remotely, across 15 billion miles of vacuum, using commands that took nearly a full day to arrive, on a computer system built before the personal computer existed. In March 2024, JPL engineers traced the November failure to one chip. The chip stored a portion of the FDS memory that included some of the computer's own software code. The loss of that code rendered the data stream unusable. The failed component was identified as a single RCA CD461A CMOS SRAM chip, which held 256 words of FDS memory. Whether it had worn out after 46 years aloft or been struck by a cosmic ray particle could not be determined, and made no practical difference. The chip was dead, and it could not be replaced. What followed was one of the most extraordinary acts of engineering in the history of space exploration, and almost nobody in the mainstream media gave it the attention it deserved. The team would relocate the corrupted code to spare corners of the FDS memory. But no single block was large enough to hold it all, so the engineers did something that sounds almost impossibly delicate. They took the affected software code, sliced it into fragments small enough to fit into whatever empty pockets of memory they could find scattered throughout the system, rewrote each fragment so that the pieces could still communicate with each other and function as a unified whole, and then, only then, did they beam this surgical repair across 15 billion miles of interstellar space and wait. They deleted routines the spacecraft no longer needed, including software from its 1979 Jupiter flyby, to clear room. They deleted the ghost of Jupiter to make space for survival. They sent the first part of that fix on April 18, 2024. About 22. 5 hours later, it reached the spacecraft, and on April 20th, Voyager 1 returned readable engineering data for the first time in 5 months. When the signal came back clean, the JPL conference room reportedly erupted. Because these engineers, many of them young enough to be the grandchildren of the people who originally built this machine, had just performed remote surgery on a 1970s computer floating in interstellar space, using tools and techniques that didn't even exist when the patient was born. That is what it takes to keep Voyager 1 alive. That is the kind of impossible daily commitment that this mission demands from the humans who have dedicated their careers to it. But the crisis of 2023 and 2024 also accelerated a painful reality that was already well underway. The instruments are being shut down one by one in a slow countdown that everyone at JPL understands, but nobody likes to talk about openly. The cameras went in 1990. The plasma science instrument degraded to the point of uselessness years back. In February 2025, JPL turned off the cosmic ray subsystem, the suite of 3 telescopes that had helped determine exactly when and where Voyager 1 crossed the heliopause. That left 3 instruments running: the magnetometer, the plasma wave subsystem, and the low-energy charged particle detector. And then even that number began to shrink. In 2025, the team switched off Voyager 1's cosmic ray subsystem, the very instrument that had helped confirm the crossing into interstellar space a decade earlier, purely to save power. An instrument that made history, switched off not because it failed, but because Voyager 1 simply cannot afford to power everything anymore. The physics of radioactive decay does not negotiate. The plutonium is running out, and every instrument that stays on is drawing from a reserve that will eventually hit 0. What most people are not seeing is that this is not a story of failure. This is a story of something profound and deeply human, the act of choosing what to preserve when you cannot preserve everything. NASA is making the same decision a family makes when a loved one is on life support and the resources are finite. What do we keep? What do we let go? What matters most? And the answer, in Voyager's case, is the magnetometer and the plasma wave subsystem. The 2 instruments that are mapping the interstellar medium, measuring a region of space that no telescope on Earth or in orbit can ever observe, because telescopes look across space, while Voyager is inside the space we have never touched before. Together, these 2 instruments are mapping a region of space that no other telescope or probe can observe. The data is sparse, but Voyager 1's magnetometer measures the direction and strength of the local magnetic field, while the plasma wave subsystem detects electron density by listening for plasma oscillations. Think about what that means for science. We are learning, in real time, what the space between stars actually feels like from the inside. Not modeled, not theorized, measured by a machine built during the Ford administration, still functioning, still sending home data that rewrites textbooks. And all of this makes the camera question even more haunting. Because if you step back and ask yourself what image Voyager 1 would capture if its cameras could somehow be turned on today, the answer is both logical and devastating. According to what astronomers have carefully calculated, the view from Voyager's current position would show our sun reduced to just the brightest star in the sky, still unmistakably the most luminous point in its field of view, but no longer a disk, no longer a source of warmth, no longer a sun in any meaningful experiential sense, just a very bright dot among thousands of other dots. Earth would be invisible, completely invisible, far too small and far too faint to be detected by any camera Voyager carries, even if those cameras were in perfect working order. The solar system itself would appear simply as a field of faint points of light, indistinguishable from the broader stellar background without careful mathematical analysis. There would be no dramatic image, no awe-inspiring vista, just stars, an ocean of ancient light from suns that are themselves billions of miles away, and in the middle of it all, one point of light, our sun, that only a human being who knew what they were looking for would recognize as home. This is not chaos. This is perspective. And it is the same perspective Carl Sagan tried to give us in 1990, when he convinced NASA to turn the camera around one final time and capture the dot. He wrote afterward that the image underscored our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we have ever known. He understood that the most important thing Voyager could do with its camera was not to photograph Jupiter or Saturn or the rings or the moons, as spectacular as all of that was. The most important thing it could do was to turn around and show us ourselves. And then the camera went off. And it has been off for 36 years. Now think about the timing of where we are in 2026. On November 18th, 2026, Voyager 1 becomes the first machine ever to be a full light day away from Earth. One light day. The signal from that machine will take 24 full hours to reach us at the speed of light. That milestone, the first human-made object to cross the threshold of one light day from its origin, is coming within months. And the spacecraft that will cross that boundary is the same one that looked back at us in 1990, the same one that went silent in 2023 and was brought back from the edge by engineers performing the equivalent of open-heart surgery via telegram, the same one that is slowly, instrument by instrument, powering down its own systems to stay alive just a little longer. What does it mean that the thing most people associate with Voyager 1, the camera, the image, the pale blue dot, has been dark for over 3 decades? What does it mean that a machine we still call the most distant human artifact ever created has been blind since 1990? And what does it mean that even as it goes blind and its instruments are switched off one by one, it keeps going? It keeps transmitting. It keeps measuring the invisible boundaries of the space between stars. It refuses to stop. According to informed sources within the scientific community who have followed this mission for decades, there is something about Voyager that transcends its technical specifications. It is not simply a probe. It carries a golden phonograph record, the Golden Record, containing music from dozens of human cultures, greetings in 55 languages, the sounds of Earth's oceans and winds and thunder and animals, and 115 images encoded in analog format, including a photograph of a man and a woman, a diagram showing where Earth is in the galaxy, and mathematical information that would allow any civilization capable of finding it to decode everything else. We sent Voyager out into the dark not just as a scientific instrument, but as a message, as an introduction. As a prayer, almost. The closest thing to a letter in a bottle that a spacefaring civilization can write. And that machine, the one carrying our message to the stars, is the same machine that went blind in 1990. The same machine that started speaking gibberish in 2023. The same machine that a team of engineers in Southern California fixed using software archaeology and pure stubborn brilliance. The same machine that is still out there, right now in the space between stars, measuring the magnetic field of the interstellar medium with 2 instruments that have been running continuously for nearly 5 decades. The real story is not just that the camera turned around in 1990. The real story is what happened after. The real story is that a machine built for a 4-year mission has been operating for 49 years, that a memory chip failed 15 billion miles away and humans fixed it, that the solar system's most distant ambassador is now approaching a milestone no human-made object has ever reached, that the scientists who keep it alive are working with code older than most of them are, diagnosing problems with a 45-hour round-trip communication delay, and still, somehow, getting it right. But here's the question that nobody is fully prepared to answer. When Voyager 1 finally goes silent, and it will, possibly sometime in the late 2030s, when even the 2 remaining instruments can no longer be powered, what happens to the Golden Record? What happens to the message we sent? The spacecraft will keep traveling. There is nothing in interstellar space to slow it down. No atmosphere, no friction, no obstacles in any direction that matter. It will continue at roughly 38,000 miles per hour essentially forever, or until something intercepts it, something changes its trajectory, or the sun itself ceases to exist. Scientists estimate it will take approximately 40,000 years for Voyager 1 to make a close approach to another star system. 40,000 years, longer than all of recorded human history, multiplied many times over. Will humanity still exist in 40,000 years? Will whatever civilization finds it, if any civilization ever does, be able to decode the Golden Record? Will they understand the mathematical diagrams, recognize the pulsars used as navigational markers, play the music and hear something in it that resonates with whatever they experience as beauty? Or will Voyager drift through the galaxy for billions of years, carrying its message in silence, forever undiscovered? These are not small questions, and they are questions that Voyager 1 forces us to ask every time we revisit its story. Every time we remember that a machine we built turned around, looked back at us, captured our smallness in a single frame, and then went dark. The camera has been off for 36 years. 2 instruments remain. 1 light day milestone is approaching. The plutonium is still decaying. The signal is still coming home, and somewhere in the interstellar dark, farther from Earth than anything we have ever sent, a golden record is playing to no one, for now.